Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, and welcome back to week 5 of part 2 of Fundamentals of Atomic Force Microscopy. We're going to, in this last week, focus on some additional topics that can be considered as extensions of the methods that we have studied in detail. In the last class, we were focusing a lot on the use of frequency-modulated AFM and AM AFM to reconstruct the interaction forces between the tip and the sample. What we're going to focus on during this week are extensions of dynamic AFM to measure electrostatic forces, to measure magnetic forces, and to understand what happens when dynamic AFM is actually taken into liquids, as often done to study biological samples. This is the last week of classes, and we are trying to cover more than one topic. As a result, we will not be able to go as much in detail into each one of those topics, and I hope that the references we provide and the material in the appendix is going to be sufficient for those of you who want to dig a little deeper into each of those topics. We're going to start with electrostatic force microscopy methods, which is an umbrella term, really, where one uses conducting AFM tips, whether they're metal-coated or they're highly doped semiconductors. When one uses these kind of tips to measure a whole variety of electrical properties of the substrate, including local charges, dielectric constants, film thickness of dielectric layers, photoinduced voltage, and the contact potential difference or the work function of conductors as well. There's also a reason why I use methods, plural, because there are actually not one method, but more than one methods of electrostatic force microscopy. So what we'll try to focus on in this module is understanding how the Kelvin probe microscopy method is used to understand work function differences on substrates. Now, in order to do so, we need to do a little backup, and I'm going to go to the board now and talk a little bit about the electronic band structure of crystalline solids. Before we go to understand contact potential difference, it's important to just go over the basic electronic structure of crystalline materials, which are very well modeled by solving the Schrödinger equation within a periodic potential within the crystalline lattice of the solid. At the end of the day, what comes out of such calculations is what's called a band structure, which basically tells us what are the allowable energy levels that electrons are allowed to sit in or move in within the solid. For a conductor, there's energy states within what's called the valence band, where the electrons remain confined to the vicinity of the atom to which they're closest to. When one goes to higher energies, one goes into the conduction band, where the electrons then are non-localized and they can move all over the lattice. And this is what leads to conduction properties of a conductor or a metal. For metals, the conduction energy band and the valence band actually overlap. And for a semiconductor, they don't overlap, and there's an energy gap, a band gap in between. Now, the band structure just tells us about the probable or possible energy states that electrons can sit in, or the allowable states they can sit in within a solid. To really understand which ones of the states are actually occupied at room temperature, one needs to go to Fermi-Dirac statistics, which roughly tells us that there is, for each conductor, there is an intrinsic Fermi level, which tells us the energy level below which most of the states are actually occupied by electrons, and above the Fermi level, the states are actually not occupied. So, in the context of work function of conductors and metals, we can go back to this slide and imagine that we are dealing with a situation where we have a conducting sample and we have a conducting tip. The tip is red and the substrate is actually blue. What's shown here are the energy states possible within the tip and the substrate. both have their own Fermi levels, because the Fermi level is an intrinsic property of the chemical composition of the conductor, and those two can be very different. The other important thing to keep in mind in the panel on the top left is we're talking about a reference energy level, which is going to be the E vacuum, EVAC, and the energy levels of the Fermi level and below are shown on this graph, all relative to the EVAC. Now, EVAC is effectively the energy level at which the electron can be considered as being dissociated with the solid and free in space, obeying the laws of particle mechanics with certain charges. Whereas when the energy is below EVAC, it can be considered as being associated in some way with the solids and being governed by the laws of quantum mechanics. Now, another important thing that is shown in the panel on the top left is the fact that when you refer both the tip and the sample to the same vacuum energy, the Fermi levels are different, and so the difference between the Fermi level and the vacuum energy level is called the work function of the particular metal or conductor. The work function itself has a nice physical meaning. It refers to the energy that needs to be applied to pull an electron out from the Fermi level to take it out into space. And this is, in basic physics, it's regarded as the main reason why electrons don't just fall out of conducting surfaces, because there's an energy barrier, which is basically the work function that has to be overcome for the electrons to be pulled out of the bulk solid and pulled out into space. Now, what we're going to show is that how this difference in work function between the tip and the sample leads to a potential difference between the tip and the sample when they're connected together. So on the panel B, you see that when these two are joined together with an electrical connection, the tip and the sample, what ends up happening is that the energy of the electrons in the substrate and the tip are going to equalize, as shown in the panel on the bottom C. And that equalization is accompanied by a general lowering of energy, in this case on the substrate, such that the energy levels of the electrons in both the tip and the sample are the same, the maximum energies. That is accomplished by a reduction in energy level, in this case in the substrate, by an amount equal to delta phi, which is the difference in work function between the tip and the sample. Delta phi can be regarded as being equal to E times VCPD. E is the charge of a single electron. VCPD is what's called the contact potential difference. As a result, what ends up happening is we end up getting now voltage difference that arises between the tip and the sample. If you have two conductors with a voltage difference between them, what comes out of this is basically an electric field E. What one can do to measure this contact potential difference VCPD is to apply an external bias voltage, as shown in the panel on the bottom right, to bring the energy of the substrate back up in a manner such that the electric field is actually nullified or made zero. So you would add a voltage bias to counter the VCPD such that the tip and the sample end up being at the same potential and there's no electric field between them. The voltage you need to apply for that to happen is then going to be negative times the VCPD. So this is the basic idea of trying to null the electric field and figuring out the voltage it takes to null the electric field, which then, when multiplied with E, the charge of a single electron, is going to give us the contact potential, or is going to give us the work function difference between the tip and the sample. This is the basic idea, and it's an important property of conductors that is not very easily accessible using other measurements. And this was of a lot of interest in the 19th century, and Lord Kelvin was the first one who tried to come up with a method to solve the problem, which is why the techniques that evolved from that are called Kelvin probe microscope techniques. The basic idea that Lord Kelvin proposed was to bring a reference material and a substrate very close to each other and measure the current that's generated when you put these two in contact. And if you know the current, you can use simple results that are shown here to figure out the connection between the current and the work function difference between the two materials. An improvement on this technique was made by William Zisman in 1932, where the concept of a vibrating electrode was introduced. This was a very useful technique because it really ended up improving a lot the sensitivity of the measurement of work function difference between the tip and the sample. Here the idea is that if you want to measure the work function of a conducting substrate, you take a conducting reference material which has a known work function. This could be platinum or some material whose work function everyone agrees on. And you would mechanically move this up and down near the substrate that you're trying to measure, and you'd link these two up with a wire or connect them electrically and measure the current that flows between the reference and the substrate. Now, how this method would work then is in the following fashion. What I've shown on the top is a simple expression for the capacitance of two parallel plates. Again, you can look at the appendix for some more details on this. But the key thing is the gap D between the reference and the substrate is oscillated. The capacitance is going to change with time. And the capacitance is, of course, equal to the induced charge Q, the uppercase Q, divided by VCPD. Which is the contact potential difference. And so the current that's induced is going to be as shown, dq dt, and since the voltage VCPD is constant, the contact potential difference is constant, the current comes out due to dc dt, the changing capacitance. The capacitance in turn is changing at the frequency at which the reference is oscillated, and the magnitude of the current therefore is proportional to VCPD. So the idea is, in this case, that if we were to apply a counter bias to counter the contact potential difference, you would do so by measuring the current, an AC current, not a DC current, but an AC current, at a frequency at which this system is excited. And then you would measure the amplitude of that current and apply DC bias to counter the contact potential difference until it becomes zero. So this idea moved the measurement of contact potential difference from static currents or decaying currents to AC currents, which are much easier to measure and can be measured with much more sensitivity. And using this technique, though, the macroscale contact potential measurements, one could measure work functions or contact potentials of the order of 1 millivolt resolution. Now, not surprisingly, very soon after that, very soon after the invention of the scanning probe microscope, there was a lot of interest in seeing if one could use the AFM cantilever as the reference electrode to measure the work function of a substrate. Before we go ahead with a scheme by which this could be done, I want to highlight a certain practical complication that arises when one tries these kind of techniques on realistic samples. Now, in the case where one prepares a sample, which is, very clean conductors with very little contamination, in that case, the measurement of the contact potential difference is telling us directly about the difference in work function between the tip and the sample. In many samples, however, one could have situations where the conductor actually has contaminants on top. You could have surfaces where it's conducting in some places, and then you have insulators or dielectrics in other places. Those dielectrics could in turn have trapped charges on them. So the measurement of contact potential difference in such complicated samples is not going to give us the work function of the sample. One needs to recognize that effectively what one is trying to do at the end of the day is trying to null the electric field between the tip and the sample. So when you bring a tip close to the sample, electric fields naturally develop between the tip and the sample due to more than one reason, not just the work function, but you could have charges in the substrate, other effects. And you can correlate the measured contact potential difference to the work function difference only if once you've made sure that all these other confounding factors are not involved in your particular tip and sample combination. All right, so one can think of trying to use Kelvin probe microscopy in the following fashion. We have a sample which has a potential at every point x and y on the sample. This mimics the fact that as the tip goes over the sample, it feels different electrostatic forces at different points in the sample. If it's a nice conducting sample, then this basically reflects the changing values of work function over a sample, for example. In the case of more complicated substrates, it's just a way to capture the fact that the electric fields are different at different points in the sample. So what we want to do is to measure this effective voltage at every point in the sample, X and Y. The way to do it using dynamic AFM or Kelvin probe techniques is to apply two kinds of excitation. One is a mechanical excitation, one is an electrical excitation. The mechanical excitation is applied through base excitation, dither piezo excitation at a frequency omega that drives the cantilever into resonance. There's an amplitude and phase corresponding to it, which can be used for feedback and tracking the topography of the sample. In addition, one applies an electrical excitation to the conducting cantilever, which comprises a DC component and an AC component whose frequency is omega elec. Usually, the electrical excitation frequency is much smaller than the mechanical excitation frequency and is typically of the order of 5 to 10 kilohertz. Now, when one applies this voltage to the cantilever, you can see that there's going to be at every point of the sample a different value of voltage difference between the tip and the sample, which is given by the difference of V sub S with this VDC and VAC term. So the idea here is then to scan the sample using observables of the mechanical excitation frequency, but use the observables at the electrical excitation frequency to measure the local electrical properties of the sample. To understand how that would work, we start by an expression that tells us about the electrostatic force applied to the cantilever due to this difference in potential between the tip and the sample. An expression for the electrostatic force is derived in the appendix. It is based on the expression for energy in a capacitor. The energy in a capacitor, stored energy in a capacitor is 1/2 CV squared, where C is the capacitance, delta V is the voltage difference between the tip and the sample. The gradient, the vertical gradient of the capacitance gives us the electrostatic force, F electrostatic, as shown here. And in this expression, we go in and plug in the delta V expression from the previous slide, and we expand the terms, and we see that upon expanding the terms, we get three different distinct terms. The first would be a purely DC term, which involves the square of the difference of Vs and the DC bias voltage. There's also a term which involves sine squared omega elec t. Sine squared can be written using trigonometric identities as 1 plus or 1 minus cosine 2 omega elec divided by 2. That's why that term, the square term, is regarded as a term that gives a harmonic signal at 2 times the omega elec. The last term, the third term, is actually a cross term that is at omega elec, and the magnitude of that third term is governed by the difference of the sample voltage and sample potential and the DC bias applied to the cantilever. Now, as one breaks this up, one realizes that there is going to be therefore a forcing, electrostatic forcing, that happens at omega elec, at the electrical excitation frequency, which is shown below. And there's also going to be an excitation, a force applied on the cantilever at 2 times omega elec. Now, when you take a cantilever and you apply 2 frequencies in addition to the mechanical frequency, we're just looking at the forces that come from the electrical excitation on the sample. One can easily derive, as shown in the appendix, that the tip motion due to the electrical interaction also consists of motion at omega elec and motion at 2 omega elec. The motion at omega elec is basically an amplitude and a phase at the electrical excitation frequency that is picked up in the mechanical motion of the cantilever, and also an amplitude and phase that's picked up at 2 times the omega elec. This is related to the electrostatic force applied by the expression shown on the right, which is related to the cantilever stiffness K. Again, this is derived in some more detail within the appendix. So the idea is that one is measuring the tip motion at omega elec and at 2 omega elec. So all we have to do at every point in the sample is implement a feedback loop whereby one changes the DC voltage on the tip to make the voltage response, or make the cantilever response at omega elec equal to 0. By doing so, we're effectively saying that the electrostatic force at omega elec has become 0, and that's only possible if the DC voltage has now equaled the Vs, or the voltage on the sample. So we're effectively nulling the voltage on the sample. And we can map, so the VDC can then be mapped over the sample, and we would effectively get a contact potential difference map over the sample. There is a third channel here, which would be the 2 omega elec channel. If one were to measure the amplitude there, you can see that the response at 2 omega elec is actually related to the quantity DC, the gradient of the capacitance. And the gradient of the capacitance, as shown in the appendix, is related actually to the dielectric constant of the sample, amongst other things. So the channels we fundamentally have in electrostatic force measurements is a channel at omega elec and a channel at 2 omega elec. We implement an electrical feedback on the omega elec channel to null the vibration at that frequency and thereby derive the contact potential difference at every point in the sample. What I've shown here is a schematic sketch of how the Kelvin probe force microscope works. We have a sample, we have a cantilever. We need at least 2 lock-in amplifiers to implement this. The measured AC deflection goes into 2 lock-in amplifiers. One lock-in amplifier measures the amplitude and phase at the mechanical excitation frequency omega. The other lock-in amplifier measures the amplitude and phase at the electrical excitation frequency. The first lock-in amplifier is used to implement feedback to track the topography of the sample. The second lock-in amplifier measures the amplitude and phase of the cantilever response and implements a feedback loop to change the DC bias to actually null the signal, the vibration response at that frequency. And the value of the bias voltage required to null the vibration signal at omega elec is recorded as the contact potential difference at every point on the sample. One could use a third lock-in amplifier and track the 2 omega component as well, which would give us a measure of the gradient of capacitance. So this technique was, with the 2 lock-in amplifiers, was effectively implemented, in this early paper in 1991 by Vikram Singhe's group. And what I show you here is the first results that were published here on different metals, sitting on different metal substrates. So, for example, if one were to look at figures C and D, we have an example of a gold strip sitting on platinum, and you can, or platinum actually deposited on gold, and you can see in C that there's a topography difference between these 2 materials. But then if you go to the contact potential difference, which is shown in D, you can see a very clear contact potential difference of 90 millivolts in this case between gold and platinum. And then in E and F, the topography and the contact potential difference between palladium and gold is also shown. So the really neat thing about this technique when it was published was the great sensitivity that was afforded to this measurement by using the resonance of the cantilever and using AC excitation to measure the electrostatic fields. And it was shown that one could, using this technique, be able to detect a 0.1 millivolt difference in contact potential difference over the sample, which would be a significant improvement over the macroscale measurements that were implemented earlier. The other advantage, of course, is this is a scanning tool, so you can actually map out with very high resolution changes in these properties over the sample. So with that, we're going to stop this particular module today and continue talking more about some subtleties with electrostatic force microscopy that need to be considered. Thank you very much.